For this question, we've been asked to find the range at which a projectile can reach passing over a mountain and the range at which a vessel would be safe between this minimum range and the mountain. So, initially to find this, we'll need to use a bit of trigonometry to find the components of the initial velocity. So, using this here, we can see that our x component of velocity will be equal to 250 cos theta, and our y component will be equal to 250 sine theta. Now, we're going to use two equations throughout the course of this. One is the displacement for y, which is equal to ut plus a half at squared, and we're going to use our displacement for x, which is s equal to ut. Now, when sx is equal to 2,500, sy is equal to 1,800. So all that's saying is, when we're out here at 2,500 at the peak of the mountain, our y value must be 1,800 to clear the mountain. Now, we're going to get, if we substitute these values into our second equation, we'll get 2,500 is equal to 250 cos theta t. Now t, if we rearrange this for t, we get t is equal to 10 over cos theta. Now this is going to be our third equation here. Now, we're going to sub our third equation into our first equation. So we're going to end up with 1,800 equal to a half minus 9.8 times 10 over cos squared. So then we're going to add on 250 sine theta times 10 over cos theta. Now if we follow this down, we're going to get 1,800 is equal to minus 490 over cos squared plus 2,500 tan theta. That's just because we've got sine over cos here. Now following this down further, we're going to move everything over to the left to get ourselves a quadratic. So we've got 490 sec squared theta minus 2,500 tan theta plus 1,800 equals 0. Now sec squared theta also equals tan squared plus 1. So we're going to substitute that in here, and we've got 490 outside of 1 plus tan squared theta minus 2,500 tan plus 1,800 equals 0. Now you can rearrange that, expanding out this bracket here, we'll end up with 490 tan squared theta minus 2,500 tan theta plus 2,290 equals 0. Now, if we let x equal tan theta, we'll end up with a quadratic formula just here. We'll end up with a quadratic, and we're going to use our quadratic formula to then find the angle, both the minimum and the maximum angle. So we're going to substitute all of that in here. So we've got 2,500 plus minus the square root of 2,500 squared minus 4 times 490 times 2,290 all over 2 times 490. Now, once we finish that, we calculate that, we'll get x is equal to 3.9 or 1.2. Now, substituting back in our tan theta value for x, we'll get theta is equal to inverse tan 3.9, which is in turn equal to 75.62 degrees. Now, this is following down 1.2, we'll get theta is equal to tan minus 1, 1.2, which is then equal to 50.14 degrees. This provides us with our maximum and minimum angles, therefore time may be found. So we're going to use our displacement for y formula again. We're going to set it to 0 to find when the projectile will hit the ground. So it's going to be here, here, and here it'll be on the ground. So with that knowledge, we're going to head into this one. And we've got 0 is equal to a half outside of minus 9.8 times t squared plus 250 sine theta t. Now we'll pull the t's out the front of that and we'll get t outside of minus 4.9 t plus 250 sine 50.14. Now we're going to use 50.14 first, so we're going to use our minimum angle to find out what time it will hit the ground. So with that in mind, t at this angle will equal 0, as we can see out the front, but we aren't looking for the initial, we're looking for the actual range. So we'll go 0 is equal to minus 4.9t plus 250 sine 50.14, and we'll rearrange that again, and what we'll find is t is equal to 39.1 seconds at 50 degrees 0.14. So it takes 39.1 seconds for the projectile to hit the ground again. Now we're going to do that again for 75.62 degrees now to find our maximum angle. So 0 is equal to minus 4.9t plus 250 sine 75.62 degrees. And we'll find that t is equal to 49.4 seconds. Now, we're going to use these times and our theta values and substitute them back into the Sx formula to find our total range that the projectile goes. So, what that gives us is Sx is equal to 250 cos 75.62 times 49.4, and we find that it's equal to 3,070 meters. While if we do it for our 50.14, for theta equals 50.14 degrees, we'll get Sx is equal to 250 cos 50.14 times 39.1. And that gives us 6,270 meters. Now, we're looking for where the vessel is safe. So we're looking for this part of the drawing here between the shore and the minimum distance the projectile can hit on the right side of the mountain. Now, if we do that, we've got 3,070 meters minus the 2,800, which is the length to the peak of the mountain, plus the right-hand side of the mountain, and it equals 270 meters. So the vessel is safe within 270 meters to the right of the island. Thank you.